So, the wave function, what is it? Well, it's a mathematical function that describes the properties of the electron. Now, everything I've done up till now, we've talked about in terms of x, y, z, right? Cartesian coordinates. And of course, that's what you're much more familiar with. However, when we're talking about the wave function, it is far more convenient for us to use so-called spherical coordinates. Okay, so that's instead of talking about it in terms of how far a particular point is on the wave function in terms of across and up and in and out, we talk about how far it is and then its angle relative to these various axes. Okay, now this enables us to separate the wave function into two bits, so-called radial wave function, which is just to do with r, and then the angular wave function, which just has to do with those angles. Okay, and this gives us a lot of mathematical flexibility that you're not necessarily going to give a flying poop about right now, but will be really, really important to you as we go in there further. And it is important that we just throw at you right now, not in any way that I expect you to reproduce these or anything, but just so you can see where some of those orbital shapes that should have been familiar with you to you coming in from A level actually come from. Focusing in first of all on the radial wave function. Okay, now remember, the wave function is this long, complicated mathematical function that is describing the electron. Okay, where the electron is, the properties of the electron, and so on. Okay, and so we can describe the space, if you like, that the electron is probably going to be found in terms of this, the wave function, a mathematical function. We're splitting up into having an r component, how far is the electron from the nucleus, and then the angular component, which describes, as we'll see in a minute, the shape. So if we look first of all at the 1s orbital, it's the one where n is 1, the quantum number is 1, and principal quantum number 1, and L is 0. This is what it looks like. It looks pretty innocuous, doesn't it? But that's what the graph of that wave function looks like in terms of just the radial part of it. Okay. By the way, taking this picture and one previously from your textbook Chemistry Cubed that I hope you are using. If we go to the 2s orbital, it gets a little bit scummier. Okay. And what we see is we actually see that there is a node here as it goes from positive to negative, this node at which the wave function is actually 0. Okay, now this might not make much sense to you if you think about it in one term, but this is just how far we're going away from the nucleus. This is the sign of that mathematical function here, positive and negative, once it passes through the node. Okay, it's not saying suddenly you've got a negative electron or antimatter or anything silly like that. It's just saying that this mathematical function, when applied to the 2s orbital with n of 2 and L of 0, has both positive and negative bits. And we go to the 3s orbital, it's actually got even more than that. It's got positive at the start and then it goes through 0, so it has a node, and then it's negative, and then it comes back up, has another node, and then it's positive again. Okay, one feature of 3s orbitals is they have n-1 radial nodes, so to speak, bits where it's 0. So 1s, n is 1, no radial nodes, n-1 is 0. 2s, the graph, a radial function, has got one radial node, so it changes sign once, and then n is 3, n-1 is 2. It has two radial nodes, so it changes sign twice. Okay. Go to p orbitals. These are what these look like. So the 2p orbital. Now notice p orbitals, their value at r of 0 is 0. Okay, s orbitals had a definite value, this function, right? It's a mathematical function when r was 0. But all other orbitals, the 2p, and as we'll see in a minute, the d orbitals, they all start at 0. They have a 0 value at the nucleus. Okay, here's the 2p, goes up and comes back down again. 3p goes up, comes down, has a node, and then levels off. Okay, and generally your p orbitals have n-2 radial nodes. So that's one way in which you can distinguish between, say, the 3s and the 3p. The 3s has got two nodes, the 3p has one node. And guess how many the 3d has? Yeah, no nodes. Okay, because d orbitals have n-3 radial nodes. So if I went on and I didn't say the 4d orbital, or the book had done the 4d orbital, it would look something akin to this. Again, d orbitals start at 0, and go up and then start coming down and to head towards 0 as r gets bigger and bigger and bigger, and it's just a question of whether or not they cut the axis and how often they cut the axis as to what the value is of n. Now those are pretty, but they don't actually tell us very much. So only in quantum chemistry courses will you plot out the value of the radial wave function against r, the distance that the electron is away from the nucleus. Much more important is so-called r squared, or if we think about it, just this, the wave function squared, okay, but thinking of it again just in terms of the radial wavelength. This actually has to do with the probability of finding a particular electron, okay, and that's, if you think about it, how we talked a lot of times about what the wave function is really going to be telling us, okay. And when we plot out, for example, the 1s and the 2s orbital, we can see that we have all of them positive, okay. Well, of course, if there's a probability, you can't have a negative probability of finding something. It's either a positive probability or a 0 probability, okay. And so this r squared value, this probability, is one that's a lot more useful to us than just the straight r. But even then, there are issues with just interpreting it straight off like this. You can see that, for example, the 2s has got an infinite probability, if we believe in that, of finding the electron at the nucleus. Well, obviously that's not true, right? So there's something wrong with just thinking about squaring the radial function. Something, however, that is important associated with squaring the radial function is that when you add up all the probabilities, it has to be 1, right? An electron's got to be somewhere. So if you take all the places it could be, add up the probability of it being there, and you're going to get 1. Now, this is called normalizing a wave function, and you don't have to worry about it anymore now. You certainly don't have to worry about this disgusting looking equation, but essentially what it's saying is that when you come up with your mathematical equation that describes the electron, when you come up with your wave function, you have to have it in some sense that when you square it and integrate it, right, that gets 1. And you'll hear talk about this normalization of wave functions many times as you go through these quantum courses. Essentially, it just means you adjust the wave function when you've got it so that when you integrate it, you get 1. And it's not that hard to do. In fact, this is by far the nastiest aspect associated with it. Anyway, we would like to talk about probability. This r squared straightforwardly doesn't get it to us. So we have to go to the radial distribution function, and that describes the most probable distance of the electron from the nucleus. It helps us determine that, and mathematically we just take our wave function, multiply it by 4 pi r squared, plot this against r, and when we do that, this is what we get nicely from our Chemistry Cube textbook. So here is what the 1s probability looks like. 0 probability of being at the nucleus, close to 0 probability of being miles away, goes up and down, and here is the maximum for it, okay. Looking at the 2s and the 2p, here's the 2s, has a little node there, okay, because remember the s has got a radial node, okay, and then maxes out. Here's the 2p, no node, maxes out. 3s in red, 1, 2 nodes, so 3 little humps there. The 3p in blue has got 1 node. The 3d has got 0 nodes. You don't count starting at 0 as a node, by the way, for these things. Okay, so this is what the radial distribution function is going to look like. Okay, now this is not the shape of the orbital. Okay, this is just what the probability is going to be of an electron being there as you get a certain distance away from the nucleus. The shape comes from the angular wave function, okay? This gets really complicated, so I'm not going to do more than discuss a couple of them. The angular wave function for s orbitals is constant. They're spherical, okay? And so when we think about an s orbital, it's a sphere as you go all the way out. Its shape is a shape, the geometry as you go up from the nucleus is the sphere. We're going to always worry about the boundary surface of an orbital in terms of what its shape is. usually the boundary surface is defined as how far out are you until the shape defined, the volume defined, covers 95% of the probability of the electron being in there. So an s orbital, 95% of the time, electron's going to be in that sphere. However, as you go further out than that, it can go further out than that, it's just there's not the big chance of doing it. Okay. Think about the PZ orbitals. They have a cosine theta dependence. Now, I hope you've done some trigonometry. Cosines can be positive or negative. So what that means is that the orbital can be positive or negative, right? Not that the electron is suddenly positive or negative, but the wave function that describes it is positive or negative. And of course, I hope you're used to seeing it like this, two different colors. You might have plus, you might have minus in there. Notice that we have this point in the middle, 0. That's an angular node because it's a 0 point when we're looking at the angular part of the wave function. And of course, s orbitals have 0 angular nodes, p orbitals 1 angular node, and d orbitals 2 angular nodes. So anyway, 11 minutes of pure torture, I'm sure, right? But what I want you getting out of this, the wave function, the thing that everything stems from, is just a mathematical function. We can split it into 2 bits, the radial, which just talks about how far the electron is from the nucleus, and the angular, which talks about the general shape of the volume associated with that particular electron. Okay, various characteristics of the radial parts and the angular parts. I want you to have seen these. I want you to be familiar with them. Heaven forbid, I do not expect you to understand where it all came from, just that you followed essentially the words that were coming out of my mouth, and there will be more layers added to that onion as you go into further modules.